In this unit, we're going to study polynomials. In this lesson, we're going to introduce factoring, and we're going to start by looking at the greatest common factor.
All right. Hi, everybody. So in this lesson, we're going to introduce factoring, and very specifically, we are going to take a look at greatest common factoring, okay? That's kind of where we start with all this. Now, before we get into this, though, we want to talk a little bit about dividing specific terms, because this is something that we're going to end up having to go over kind of and use this again and again and again as we go through factoring. Okay, it's just something that comes up an awful lot, so we want to make sure that this makes total sense to you. So when you divide terms, remember, we're going to divide the coefficients, okay, just regularly. But when we deal with the exponents, as soon as they have the same variable, and this is the base, okay, as soon as the base is the same, then we subtract the exponents. So like what you're seeing right here, you've got 6x to the m divided by 2x to the n. So 6x to the m divided by 2x to the n. We're going to divide the coefficients, okay, because the coefficients are not part of the power. They're multiplied in front, but they're not like in the base of the power there. So we don't have to do anything with that. So it's just going to be 6 divided by 2 is 3. And then x to the m minus n. We're going to talk about that a little bit more in just a bit here. So let's take a look at some of these examples here. So first of all, we've got 2 to the 5 divided by 2 cubed. Okay, so the rule tells us that we would divide the coefficients first. Now, there's no coefficients here. Don't get confused by this. The 2 is not a coefficient. In this case, the 2 is part of the power. The 2 is the base of the power. So this is 2 to the 5, whoops, divided by 2 cubed. So this will be 2 to the 5 minus 3. Well, that's 2 squared, or 4. Okay? Over in this next one here, we've got x cubed divided by x to the 4. So that's going to be x to the 3 minus 4. And 3 minus 4 is going to be negative 1. Now, there is another way that we could do this one, though, and I want to just take a moment here and talk about that. I could also see this as x cubed being x times x times x. So 3 factors of x in the numerator, and then x to the 4 being x times x times x times x, 4 factors of x in the denominator. Now, because I've got a little bit of freedom in terms of the order of operations, multiplication and division, I can do the division here and go x divided by x is 1, x divided by x is 1, x divided by x is 1. And so what I'm going to be left with here is a 1 in the numerator, but an x in the denominator. And I want you to know that these two are the same. Okay, x to the negative 1 in the numerator is the same as an x in the denominator. Now, that is not the specific lesson that we're trying to get at in this particular topic here. I'm not actually going to take the time to really teach that. You're going to look at that a little bit later on. But I'm hoping that kind of sets a bit of the groundwork for some work that you'll do later. Here, my coefficients are 49 and 7, so 49 divided by 7 is 7. And then I've got a to the 4 over a squared, so a to the 4 minus 2. So 7 times a squared. Here, a similar sort of thing. My coefficients are 3 and 9. They are not part of the power. So 3 over 9 is the same as 1/3, so 3 in the denominator. And then I'm going to get y to the negative 4 minus, whoops, sorry, not minus y, minus 1 is what I meant to write there. Just change it really quickly to y minus 1. And it's 1 because if you see a y by itself in the denominator, it's y to the 1. So this will be y to the negative 5 over 3. But just like we saw earlier, and I want you to think about this, if when I divide powers, okay, I subtract the exponents, and I'm subtracting the exponent from the denominator from the numerator. If my exponent ends up being negative, that's because the denominator had the larger power. So again, I could probably write this as 1 over 3 y to the 5th. I could actually say that there's a y to the 5 in the denominator instead of putting y to the negative 5 in the numerator. Again, that's something that you'll take a look at a little bit more later here. Now, finally here, y cubed divided by z squared, well, okay, those two powers do not have a common base. So I'm actually going to leave it. That's it. That's as far as we'll go with that. So now let's take a quick look at factoring. With that kind of foundation set here, let's change our attention to what factoring is. Now, factoring is the reverse or the opposite of expanding, okay? It's the opposite of expanding here. So when we expand, when we're talking about polynomials here, this is distribution. And so what happens here is we go from a monomial to a polynomial. And actually, maybe when I use that word here, that might be a little bit confusing. It might be smarter for me to do this here. I'm actually going to go from a monomial to, in this case, a binomial or a trinomial or something with more than one term here. Okay, but that's all about multiplication and distribution specifically. When their pieces are multiplied together, okay, those individual pieces are called factors. Those little expressions that we multiply together are called factors. Factoring is the operation or the act of going backwards from the binomial backwards to the monomial that we apply distribution to. And the reason why we might do that is because it becomes particularly for high school math, that becomes like the primary way that we solve equations. Okay, is by factoring, by writing things out in terms of multiplication, because there's some things we can do with that are really, really helpful here. So this is really important to be able to see that. Now here's how we do it. Okay, and it can be difficult. I'm not gonna lie to you. It can be difficult. Factoring can be challenging, and that's okay. Okay, that's totally okay here. So now we're going to start off with this thing called the greatest common factoring. What the greatest common factoring is we take the coefficient that divides all of the coefficients. We're looking for that factor of the coefficients that's present in every one of the coefficients that we can see. Then we take a look and we're looking for a variable that we can see in every term. It's common to all terms. If it's even missing in just one term, it's not common. So we're looking for that variable that's common to all terms. And then what we're going to do is we're going to choose that variable and we're going to choose the smallest exponent on that variable to put on it. Because if it's the smallest one, then we can guarantee that it's going to be common to all of them. So here we go. So here's the steps here. So we're first of all going to determine the greatest common factor of the coefficients, if possible. Then we're going to determine the greatest common factor of the variables. Now remember, that's just us looking for the variables that are common to every term. And then you take out the one, or you're going to use the one with the smallest exponent to be the greatest common factor. We write that outside a bracket. And then inside the bracket, okay, this is inside, we're going to take every term that we were just looking at and we're going to divide it by that greatest common factor. So when we write it out front, okay, when we write it out front here, this is writing it out as multiplied through. But the thing is, if I'm going to write it out like that, then I need to actually divide each of those terms by that common factor so that it all makes sense here. So just for an example here, if I take a look at 6, if I want to write 6 in factored form, I know that there's a 3 that's a factor. Well, 3 times what? Well, 2. And how do I get the 2? I take 6 and divide it by that 3. That's what we're going to do here. We're going to divide every term by that greatest common factor. And then remember, you can always check to see if you've done this right. Okay, by expanding out your work, by foiling it out. If you distribute your work through, you should go right back up to the original expression there. And that will be kind of that'll tell you that you've done that correctly. Okay, so now let's take a quick look at an example here. So we're going to take this expression here, 5x to the 4 minus 10x cubed plus 35x squared. We're going to factor it out. First of all, I'm just going to look at the coefficients. Right now, that's all that's of interest to me. So the 5, 10, and 35. And I notice that every one of those is a multiple of 5. Okay, so that's going to be part of my greatest common factor. Then I'm going to take a look at all the variable parts of those terms here. And I see I've got this x to the 4, I've got an x cubed, I've got an x squared. I've got x's in all of them. That's a good sign. That means that I'm going to have a common factor with an x in it. And then I look at the exponents, x to the 4, x cubed, x squared. Well, squared, the 2, is the smallest exponent. Okay, which means there's at least 2 factors of x in every one of those. There's 4 of them. I'll write it out like this. There's 4 of them here, 3 of them here, 2 of them here. Well, there's at least 2 factors of x in all of them. So that's why I write out the x squared. Now, where do I get that x squared from up front here? Well, what I did is I took this term right here. I took the coefficient 5 divided by 5 and got 1. I took x to the 4th divided by x squared and got x squared. To get that next term, I took this term. Negative 10 divided by 5 is negative 2. X cubed divided by x squared is just x. 35x squared, 35 divided by 5 is 7. X squared divided by x squared is 1. Okay? And so that's just going to be a 7 all by itself. And that doesn't surprise me that it looks like that. Okay, so that looks pretty good here. Now, if I'm not 100% sure that I did that right, well, what I can do here is multiply it through. I can distribute this through here. So because I've got a monomial now, multiplied by a trinomial. Now, and bear in mind, this whole thing here, though, up here, this is a monomial. The way I've written it, that is a monomial. But if I want to check this out here, I'm going to multiply out the factors by simply distributing that 5x squared through that trinomial. 5x squared by x squared is going to be 5x to the 4. Okay, that's good. 5x squared multiplied by negative 2x is going to be negative 10x cubed. Okay, that's good. 5x squared times 7 is going to be 35x squared. So yeah, that works. I go right back to the original, and that's okay. Factoring should not change the value of the expression. Now, what I mean by that is if I plug in a value for x, let's see, change did do green here. If I plug a value for x into this, I should get the exact same thing by plugging a value of x into here. I'm not changing the expression. I'm just splitting it up into its different factors. It's just like when I write the number 6 or I write it as 2 times 3, I'm not changing the value. It's still the same thing. I'm just changing the way it looks. Okay, anyway, let's take a look at some examples now. So now the question here says, state the greatest common factor for each of these. Okay, so when I took a look at this first one here, it's a binomial. I've got 2x plus 4. Now notice that the x is not common to every term, so that's not the issue here. Oops, forgot. Actually, I better move that back a little bit here. There we go. The x is not common, so let's just take a look at the coefficient here. I've got a coefficient of 2 and a coefficient of 4. Well, the value that's going to be common to both of those will be 2. And if I take that out of the first term, I'm left with x. So 2x divided by 2 is just x. 4 divided by 2 is 2. And there we go. Now, this question, though, didn't require me to go that far. Okay? And actually, I'm noticing that right now. I didn't have to go that far. The question was just asking me for what's the greatest common factor. So I didn't need to do that. Let's take a look at this next one here. 3x squared plus 9. So first of all, I look at the coefficients 3 and 9. I think back, and I know that they're both multiples of 3. And then I look at both terms there and notice, hey, there's an x in both of those. So x to the, and the smallest exponent is going to be that 1. So 3x to the 1 is our greatest common factor. For this next one here, okay, I've got 12, 8, and 24. Okay, well, I want to say something like 6 at first, but then I got the 8 there, so it's got to be smaller. Well, it's got to be 4. 4 is the one that's common to all of those. And now notice that the x is not common to all three terms. There is no x here in that last term. So the greatest common factor is just that, 4. Over here, though, 12, 8, 24. So the coefficients are the same. So we're still looking at a coefficient of 4 here. But notice I've got variables in all three terms. Now let's just take a look. Is there an x in all three? Yes. What's the smallest exponent? Well, it's going to be the 1 in that last term. Is there a y in every term? Yes. And actually, it's going to be y to the 1 because in all of those terms, it's y to the 1. But notice that the z is not common to all three terms. So that is as far as you got to go. And you typically don't have to write to the exponent of 1 once you've got it there. Now, this next question here actually wants us to go one step further. It actually wants us to go through and do the factoring. Okay, so here we go. So 6n plus 9. Now, I notice that there's no common variable to both terms here, but between 6 and 9, there's a common factor of 3. So now I'm going to do the division. 6n divided by 3 is going to be 2n. 9 divided by 3 is 3. And I can verify that by simply distributing that 3 back through, and yet 3, I'm going to get 6n, and then I'm going to get 9. Perfect. Over here, between 4 and 6, well, they're both even, and that's about as good as that's going to get. So I'm going to get a common factor of 2, and there is a c in both those terms here. Now, the smallest exponent is c to the 1, so I'm going to leave it as 2 times c. Now, 4c cubed divided by 2c. Well, 4 divided by 2 is 2. C cubed divided by c is c squared. 6c to the 1 divided by 2c. So 6 divided by 2 is 3. C divided by c is 1. So it's just going to be 3 times 1, which is just 3. Now, I just want to take this moment here and make sure that everybody's on board with this. What we're doing is rewriting the exact same expression. These two are equal. So sometimes when I'm doing this, I'll get people that ask, well, wait a minute, where did the 4c cubed go? The 4c cubed is right here. It's in this multiplication. Where did the 6c go? It's right here in this multiplication. It's still there. All I've done is written it in terms of its factors. Okay, it's still the same expression. I haven't changed the value of anything. We've just changed how we're writing this. That's it. So for this next one, I've got this negative 3g plus 6. Now notice the variable is not common. I'll change the block here. Is not common to both terms there. So the g isn't going to be pulled out. But there's a 3 common to both of those. Now, when I've got it written like this, just to let you know, we don't tend to like to leave the negative in the first term. So what you'll see us do is we'll typically factor that out. And so here I've got negative 3g divided by negative 3 is just going to be g. And 6 divided by negative 3 is going to be negative 2. Now, I know it might sound weird. You're like, well, wait a minute. I still have a negative out front. Yeah, but it's not out front of this little binomial that I had created. If you didn't do that, you would have ended up with this thing looking like this: 3 times negative g plus 2. And you ask most people that are like working with math here, this looks better than this one, than the other one here, okay? So we don't typically do it like that. We typically do it like we did at first there. It's not that it's wrong to leave the negative in. It's just a formality thing. It looks better when you pull it out here. So that's going to happen over here as well. Between negative 12 and 8, and I'm just concerned about the 12 and the 8 right now, there's a 4. But I'm going to take out the negative 4. There's a d squared and a d to the 1, so I'm going to take out d to the 1. Negative 12d squared divided by negative 4d is going to be 3d minus, and then 8d divided by negative 4d is going to be negative 2. And again, I can double check that by simply multiplying that back through, and I do in fact regain those terms, negative 12d squared and 8d. Now we're going to keep going here, factoring each of these. Now these are just getting a little bit more involved here. Now, to start off with, though, for a couple of these, I'm gonna change the order. This is not written in standard form, so I'm going to just change the order slightly. So I've got a decreasing powers of the z there. Now, between -5, -10, and 5, there is a common factor of -5. I'm going to take the negative out front. But z is not common to all three terms, so that's as far as I go. So for that first term, I'm going to end up with positive z squared, because -5 divided by -5 is 1. -10 divided by -5 will be positive 2. The z stays there. And then 5 divided by -5 is -1. And there we go. For this next one here, it's already in standard form. Okay, so that's good. I like that. When I look at the three terms there, 18, 12, and 6, there's a common factor of 6. But the z is not common to all three terms, so that's okay. So 18 divided by 6 will be 3. Nothing changes with the z squared. -12 divided by 6 is -2. Nothing changes with the z. And 6 divided by 6 is 1. Now, in these last two questions, that last number there becomes a 1 here because I'm dividing that term by itself. A really common error is to make that equal to 0, for people just to cancel that out. Please pay attention to that and remember that, like 6 divided by 6 is 1. It's not 0. For this one right here, I am going to just change the order slightly here so that I've got x cubed minus 16x squared y squared minus 20x to the 1 y squared. So I'm giving priority to the x and writing it in. So like our powers here, our degrees are degree 4, and kind of degree 3 there. But I'm giving priority to the x. It just looks a little bit better. It's okay. It doesn't really matter. Now, what's common between -12, -6, -20? Well, clearly there's a negative there. I got to fiddle with 12, 16, and 20. Think about it. It's going to be 4 is the largest factor that's common to all three. And if that doesn't jump out at you immediately, that's okay. You just got to think through how you're getting those numbers there. There is an x in all three terms, and to the power of 1 seems to be the lowest. There are y's in every term, and again, that exponent also looks like 1. So here, -12 divided by -4 is going to be 3. X cubed divided by x will be x squared. Y divided by y is 1. -16 divided by that -4 will be +4. X squared divided by x is going to be x. Y squared divided by y is y. -20 divided by -4 is +5. X divided by x is 1, so that goes away. Y squared divided by y is going to be just y. And so there we go. And now finally, and I believe this one is actually okay in terms of the order there. I don't mind that. So -20, -30, -25, well, they're all negative. So I'm going to take out a negative. And yeah, between all those, looks like just -5 there. C to the 1, D to the 1, okay? Because those letters are common to all of them, but only to the power of 1. That's the highest power there. So -20 divided by -5 is going to be +4. C to the 4 divided by C will be C cubed. And then D divided by D is just going to be 1. -30 divided by that -5 out front is going to be +6. C cubed divided by C is C squared. D squared divided by D will just be D. -25 divided by -5 is +5. And then I've got this CD divided by CD. That's just going to be 1. So that's what I'm going to be left with. Good. Now, we can make this just a tad more challenging by making it so that the thing that's common is a binomial. And I know this can be challenging for people, but it's really not much different than what we've been doing here. So look at this. I've got two terms, okay? I've got this term and this term. This is a binomial. But look at it. Inside the parentheses, remember that the parentheses always enclose one thing, like one factor. I've got a y plus 1 here and a y plus 1 here. That is common. So I'm going to write that out front. y plus 1 multiplied by, well, multiplied by what? If as soon as I divide that out, what am I left with? Well, in the first term, I'm left with an x plus, and in the second term, I'm left with a 4. So when I take that out, I'm getting y plus 1 multiplied by x plus 4. Now, if you're not sure if you've done that right here, what we're going to do is we're going to distribute it, but we're going to distribute it as if this y plus 1 is a single term. So it's first of all going to get multiplied by x, and then it's going to get multiplied by the 4 here. So this is going to end up being x multiplied by y plus 1 plus 4 multiplied by y plus 1. Later on, if I absolutely needed to, I could distribute the x through, I could distribute the 4 through, but right now that's all I needed. That's all I need to show is that these two are equivalent. In this next one, similar sort of thing. I've got two terms. This is a binomial. Those parentheses are enclosing a single factor there of a plus b. So that a plus b is common. It shows up in both terms here. Now, after you divide that out, what's left? Well, what's left is 2x from the first term plus 3y. And again, just like I did with the previous one here, I could distribute that a plus b through. I don't want to split up the a plus b because in the original expression of the problem, a plus b was held together by parentheses. So I'm going to leave that together and just distribute that to both of those terms. And again, I simply regain where I started. 2x times a plus b plus 3y times a plus b. So yep, that works. I did it right.